Mark. Good evening, everyone. Mike, can you hear me okay?
Yep, you're good.
All right, we are streaming live tonight. This is great. Well, welcome everyone. I'm here to talk to you about Project Hybrid. I'm going to explain what it is, why we're doing it, and I hope to excite all of you to participate in it. Mark covered a couple of things, but typically before we have any meeting, we give a quick safety briefing. If there's a problem of any kind, earthquake, fire, flood, tornado, whatever, don't panic. Our emergency guide is out front near the board there. If you need a fire extinguisher, there's one by the front there, and there's a first aid kit in the back. If it's a life-threatening emergency, please just call 911. Our exits through the side door here, where you came in, or through the back door. The back door goes out to an active airport ramp, and so you want to watch out for any moving aircraft. You're going to exit out the door, turn left, and then make another left through the gate. Rallyport will be in the center of the parking lot.
Can you go out that door?
No, for just those two doors, yeah. Earthquake, event of earthquake, protect your head, your neck, and we'll evacuate once it's safe. Event of a fire, we'll order an evacuation. We'll meet outside in the parking lot there in the center, and then we'll call 911. Again, if it's a life-threatening medical emergency, just call 911. Tonight's schedule, I'm going to talk for about a half an hour. I'm going to introduce you to Project Hybrid. It's an idea we've been kicking around for about a year now. It's about a year in the making, and it's finally coming to fruition. Yes.
Mute your cell phones.
We'll get to that. And at about 8:15, we're going to take a 5-minute break. We're going to change presenters, and then Dr. Danny Winterhalter is going to give us our first educational seminar or talk with regard to our CubeSat project. And then hopefully afterward, we'll have a little bit of time left over. We can do a little bit of Q&A and enjoy some refreshments. Some rules of engagement for tonight's meeting. Please, first and foremost, there's a lot of us in the room, so everybody silence your cell phone. We are recording this event, and we are going to be streaming it live. There are a lot of members in the group who are unable to attend. It is a weeknight, Wednesday night, and traffic's horrible, and we all have a lot of things to do, but we are streaming it for those who are unable to attend in person. It's a small room, it echoes, so please no individual discussions. Try and hold your questions until the end. Let's give our speakers the full attention. And if there are any media or press who are invited, please, if you would, direct them to one of those 4 individuals listed. And let's get started. There's a few people that I'd like to acknowledge. I understand that I don't believe she's here yet. If you are here, raise your hand. But we are expecting a district representative for California State Senator Bob Hertzberg's office is very interested in attending tonight. Hopefully we'll see Evelyn a little bit later. Jessica Orellana is going to be visiting with us shortly. She's the LA County representative from the LA County Supervisor Sheila Kuehl's office. Tom Komarick, is Tom here yet? We got started a few minutes early, so we're still expecting a few people. Tom has agreed to join us on our Executive Advisory Committee. He is an engineer with JPL and a very, very accomplished individual. We're very fortunate to have him on our team. I believe Dean Richardson, Cap USAF representative, will be joining us remotely tonight. Hi, Dean. Gregory Chase, Lieutenant Colonel, our Vice Commander for California Wing, is with us. Lieutenant Colonel Mark Cohen, our Group 1 Commander.
Yay.
Majors Mark Butel and Greg Olson, our Commander and Deputy Commander for the facility here at Squadron 35. And finally, I'd like to thank all of you for participating, both the people here and also on the live stream. I really do appreciate everything that you do for this organization. Thousands of hours of volunteer service, that you contribute to our community, and it's very, very, very much appreciated. And I hope you enjoy tonight's talk. So let's get started. Project Hybrid, it's a 3-year project. Our goal is to design, build, and hopefully orbit a CubeSat of our own design one day. It's a 3-year project, long-term goal.
What is a CubeSat? CubeSats are very small space that orbit Earth. As you might guess, a CubeSat is shaped like a cube, about 4 inches wide, long, and deep. That's called 1 unit, or 1U. Small enough to hold in your hand, and very light, around 3 pounds. And like building blocks, units can be combined to make bigger CubeSats by stacking them into 2, 3, or even 6 units. Once in space, CubeSats can open up all kinds of tools: solar panels for power, communications antennas, telescopes, and more. CubeSats are great because they let schools, universities, and other teams launch their very own missions, and who knows what they'll discover. CubeSats are also made from standard, low-cost parts that are easy to get and tested for launch safety. Some NASA launches carry spacecraft that don't take up all of the space on their rockets, which leaves plenty of room for tiny CubeSats. Build a CubeSat, catch a rocket ride, and you become a space explorer.
Been kicking this idea around for a while, but that's a quick little 30-second introduction to a CubeSat in a nutshell there. This is a really big endeavor. It is a complicated thing that we are trying to do. This is not, for most of us, although we do have a few rocket scientists who are members, this generally is not our chosen profession. We have accountants, we have professional teachers, educators, we come from all walks of life, and what we're trying to do is incredibly difficult. What we are going to start with, in year 1, our goal is to build a computer-controlled automatic tracking system that will follow satellites as they pass overhead in orbit so that we can download telemetry. We're building a ground station. The purpose of it is so that we can work together as a team for that 1 year and build the skills that we will need to be successful in years 2 and 3. Years 2 and 3 will be dedicated to building a CubeSat of our own design. And this is going to be a very, very difficult thing to do, but it's going to be a lot of fun trying. And I think we'll be successful. So again, year 1 is tracking station. Years 2 and 3 will be dedicated to the cube. Year 1 is really the foundation for our success. If we are successful in doing this, it sets us up very nicely for years 2 and 3. All of the skills that we're going to be using to build our ground station are directly applicable to the CubeSat. If you take a look up there, we're using solar power and power budgets. This is how we power our CubeSat. We're doing 3D design and printing. Probably implement that on our CubeSat as well. Telemetry encoding and decoding, orbital mechanics, these are all lessons that will directly translate into our final goal of building a CubeSat. This is the perfect way for us to get our feet, wet and start building something tangible while we're learning all of those skills that are necessary to be successful. The other advantage is a lot of teams that have launched CubeSats in the past have been marginally successful because they have a limited ability to pull down or receive telemetry. So let's say your university or college or something of that nature, you put up your ground station and now you want to receive telemetry from your own satellite. The problem is that they only pass overhead maybe every couple days. You need multiple ground stations in order to receive telemetry throughout the life cycle of this CubeSat as it orbits overhead. So the advantage for us is we build a ground station. If we do it right, if it's durable and affordable and we can replicate it easily, imagine distributing multiple of those throughout the country at other squadrons. Now we have built ourselves, before we've started, we set ourselves up for success by learning the skills and setting up our own ground station network so that we can do command and control for our own CubeSat one day. It really, really sets us up for success. So why a CubeSat? CAP, we've been in existence now for over 75 years. We have always had essentially 3 missions: aerospace education, cadet programs, and emergency services. But over the decades, the specific way that we have implemented those 3 missions has evolved with the needs of our country. So for example, World War II, we're probably best known for coastal patrols, submarine patrols, right? Something that earned us the Congressional Gold Medal a few years ago. 1950, 1975, this was an era of the Cold War. Sputnik was launched. Although we had the same 3 missions, we were doing slightly different things. Our cadet program was huge. We were training what they called ground observers. We were looking for, low-flying enemy aircraft. There's a lot of other things that we were doing.
Radiological monitoring.
Radiological monitoring was a big one. 1975 to 2000, we have this blossoming general aviation community. Unfortunately, we're also doing a lot of search for missing aircraft, right? So search and rescue was huge. But after 2000, you had an improvement in technology, right? We have GPS, we had better navigation systems, we had more reliable aircraft, so our search and rescue mission kind of went down. But our disaster relief mission picked up. What I'm trying to get at here is that although we've had the same 3 missions, it's evolved with the needs of our country as we've gone on. As an organization, I think if we want to stay relevant, we're citizen volunteers trying to serve our communities. If we want to stay relevant, I think we have to try and anticipate, not only meet the current needs, but try and anticipate future needs of our country in order to make a meaningful contribution. And I would submit to you that in the future, the 2 things that are really going to be key are cyberspace and outer space. We're already doing a little bit of the cyberspace, right? We have the Cyber Patriot competition. I know any cadets in here that participate in Cyber Patriot? Excellent. Anybody can participate in the California Mayor's competition? Raise your hand. Excellent, excellent, thank you. So we are starting to really push on cyber security. How many of you had your identity stolen or password lost or virus, right? Cybersecurity. Now let's take a moment and consider outer space. We've heard a lot of talk recently about the formation of a space force. We don't know what form that will take. The thing that I always ask is, will there be space cadets? I don't know. Don't know how that's going to work. But there's a recognized need. You look at SpaceX down in Hawthorne. They're planning to operate and orbit thousands of microsatellites in the next few years. They're trying to build an internet, okay, with low Earth orbiting satellites. You have NOAA and the Air Force who are also looking at small, capable low Earth orbit satellites. Just as we have a need for pilots, we have a recognized need we have a shortfall of pilots now and projecting that there'll be an even bigger shortfall in the next decade. We also now have a big deficit in people that are trained in space and satellite operations. And that need is also going to grow. As all of these companies pursue these endeavors, they're going to need more and more trained people to run these systems, to engineer these systems, people who have experience. And LA County is a hotspot of that activity. Has anybody heard of Operation Moonwatch?
Moonwalk?
Moonwatch. I did a little digging. Would it surprise you to know that CAP actually has a little bit of history with regard to tracking satellites? Back in the 1950s, Operation Moonwatch. CAP was tasked to help train amateur astronomers to visually sight man-made satellites. One of the things that we did, I haven't confirmed this yet, but I'm told that one of the things we did was we towed a small 1/10 power candle power light bulb behind aircraft and trained observers to find them through their telescopes. We also had a nationwide radio network. So when these sightings were made, we helped broadcast that information to other stations so that we could, it was the beginning of trying to determine when a satellite might be in view. We were trying to keep track of these things. We didn't have instrumentation to do it. We had to do it visually. And this was the start. And CAP had a hand in this. This led to Operation Space Track, which is currently how the U.S. Air Force tracks satellites. Has anybody heard of James Westfall? Now, this is an important thing, and I want to leave you with a tidbit. This gentleman here from Oklahoma was an amateur astronomer who participated in Operation Moonwatch. This person moved to Pasadena, went to Caltech, and eventually worked on and helped engineer some of the important instruments of the Hubble Space Telescope. the things that we do in our youth can greatly influence and cause us to do really great and important things later in life. And I'd like to think that perhaps his participation in this, fostered that interest in, the Hubble telescope down the road.
Sputnik went up, and everyone's sort of running around trying to get a picture of whatever this thing is, up in the air somewhere. No known ways to do that, and I got a call. We knew a lot of people in the Boston area, scientists, because we've been at this a long time. Got a telephone call from someone in the lab who said, how would you like to get a picture of Sputnik in orbit? I said, that's a very funny joke, and how's everything? No, he said, no, seriously. And he said, well, down in Baltimore in the Knoll barn, we have a special camera which is used to track sodium vapor in the upper atmosphere. And sodium vapor lights up there, it gives a yellow radiation. So this camera is very sensitive to very dim light. He says, Sputnik goes by, it reflects light. If we knew where to look, and we happened to be calibrating the camera at 5 o'clock in the morning by accident, gee, maybe we might get a picture. I said, beautiful. There's also a Westinghouse station in Baltimore. So we sent a photographer out, and now we have to find out where's Sputnik. So we go over to Smithsonian Astrophysical Observatory, where Fred Whipple was the head of it. He's now the emeritus head, and J. Allen Hynek, who I think everyone has heard of because he was the technical advisor to Close Encounters of the Third Kind. J. Allen Hynek was at Smithsonian then. They had tracked Sputnik. So they called Baltimore, told them where to accidentally point the camera. So every morning for 3 or 4 mornings, this camera went out. There's a video output on this camera. And about the 3rd or 4th day, they get this little dot of light going across. A motion picture of Sputnik 1 in orbit before anyone in the world had a still picture. Remember, 20 years ago now, October 57 we're talking about.
This is a product of Operation Moonwatch. Yeah, so the Smithsonian was in charge of that. And the data that they used to find the Sputnik was a result of Operation Moonwatch. So, Project Hybrid. I would submit to you that this is the right project at the right time. We have the right people, the right place. All the stars are lining up, so to speak. The CubeSat format itself is widely understood. It's been adopted. It's been around for about 10 years now. And the great thing about it is that a lot of these parts are commercially available off the shelf. You can go to websites, CubeSatShop.com, and buy the components. It has become commercial off the shelf, which is really quite amazing in a short period of time. And this I really, really love. This is a company called Rocket Lab. They're building a vehicle to launch, dedicated to the purpose of launching CubeSats. Anybody taking an Uber? This is the Uber for CubeSats. Look at this. You can go to the website, rideshare, CubeSat, pick your launch. Yep, that looks good. 45 degrees.
80% book.
Pick your seat on the rocket and book it. Forget about the price for now. We'll have to work on that. This is what is happening. The industry is recognizing that CubeSats are going to be huge in our future. There are companies dedicated now to the purpose of launching them. So it's really, really exciting time. And just look in LA County, I think we're perfectly positioned. We have a large industry presence in the county. We have a lot of mentors that are available to us. We have this great facility. We're looking for an additional one as well. It plays to our strength. CAP is, we know aerospace, we know technology. This plays to our strength wonderfully. We have a motivated group of volunteers, and we are not starting from scratch. There are a lot of open source initiatives, information that has been developed over years that has now been shared freely with anybody and who chooses to use that data. The device here, this tracking satellite, is actually a fork from another project called SatNogs, which is an open sourced project. Although we've deviated significantly from their design, we didn't have to start from scratch, which is really, really wonderful. It helps accelerate our development by trying to use some of the knowledge that's already been gained. And consider the current and future need for experienced satellite operators. All of these things, they directly contribute to our 3 missions. On the emergency services side, I'm not sure, but I don't know. Maybe orbital search and rescue, I'm not sure. We'll see. But I think all of these things, opportunity means, need, and our mission directive, all of that points towards Project Hybrid. So how are we going to get there? Let's take a look at our team members. Under the authority of Mark Cohen, we've appointed Dr. Daniel Winterhalter, our executive director. Myself, good evening. I will be working on the operations, essentially trying to orchestrate the 3 teams. We're going to split off, this first year's project is going to split into 3 subject matter areas. I know I have to update this slide, but I apologize. But orbital systems, communications, and our mechanical structures group are essentially the 3 areas that we're going to work on. Michael Liu, raise your hand. Michael Liu, can I call you doctor?
Yes.
Congratulations, by the way.
Yes.
As of last Thursday, wonderful. Dr. Liu is a graduate from Stanford in physics. He is now studying electrical systems of the heart. Is that a fair? Very, very, very smart man. And he is going to head up our orbital systems group. Dr. Bahadori, Kayvon. Good evening. Kayvon comes from SpaceX. Where are you working at currently? You're here in the Valley, yes?
Yes, right down there.
Just down the road, yeah? It's wonderful. We're happy to have you. Kayvon is our Director of Communications, and he's going to be working with Captain Mike Olson, who is running our live stream this evening. Kayvon has developed communication systems for SpaceX and for his current projects as well, so perfect person to do that. Myself and Jeff Mark, raise your hand please, are going to be heading up our mechanical systems and our mechanical and electronic systems group. We also have an executive advisory committee from JPL. We have Andrew Klesch. He was unable to make it tonight, but he is. I'll let Daniel, because it's complicated, but I'll let you explain what it is that he does. But a very accomplished man.
He builds CubeSats.
He builds CubeSats essentially, but he's
In fact, he
the
built
first
the first 2 CubeSats going to Mars.
interplanetary CubeSats. That's pretty amazing. So he is on our executive advisory committee. Tom Komarick, good evening. Thank you. Also, an engineer with JPL who's agreed to join us as an advisor. And Dean Richardson, I'm so happy to see you. Thank you for coming. Dean Richardson is with Cap USAF. He is with the Pacific Liaison Region, and he is our connection to the Air Force. And so I already have one little hiccup that maybe you can help me with. We got lots of time, so to troubleshoot that, but a regulatory issue. So this is the team. This is the team that's going to help us get started. Again, we have 3 distinct areas of learning. These are the 3 groups that are going to help drive this program. First is the Mechanical Electrical Systems group. They're going to be focused on the structure, 3D printing, integrating the electronics, so the Raspberry Pi, the stepper motor controllers, etc., and the software to basically just get it moving. Okay. Our second group is the Orbital Systems group. Mike, you have a lot of work ahead of you. What we need to do, we need your team to understand orbits, do some prediction capability. Your software is going to help drive this system to be able to point and track at the satellites as they orbit overhead. That is no small feat, but very, very, very complicated. There's some advanced math in there, but it should be a lot of fun. In our communication systems, Kayvon, you got some work to do. Antenna theory and design, we're going to be building the antennas that will attach to our tracker. We're going to be using something called a software-defined radio, and this is amazing here. A USB radio receiver, controlled with software, and essentially what we're going to do is the receiver plugs into the Raspberry Pi on this device and wirelessly streams our telemetry data to a remote laptop. This thing is self-contained. We're going to be doing the acquisition of the signal and make sure that we can demodulate that data and look at the telemetry. The great thing is there are already a number of CubeSats in orbit, and they're all broadcasting this data. We just have to pull it down. So we get to benefit from the ones that are already in orbit, build our station, perhaps grow it to our own network for our own purpose, learn all of these necessary skills while we're doing it, and then apply them towards our own CubeSat in years 2 and 3. This is what a signal sounds like. was received in my backyard with a pair of rabbit ear antennas. That's from something called LilacSat. But essentially what you can see there is the signal strength of that data as it's coming in. What we're trying to do, this is some of the software that we're going to be using. We've talked to Autodesk. They're going to let us use Fusion 360 with free licenses so that we can develop the parts that are necessary. We're then going to print the parts. The next step is to slice them. Essentially, this software goes through and figures out how to build the layers to print the part out of plastic. So that's the slicer, and then this is the printer in action. And it does take some time. But ultimately what our goal is with this device, if we can pull this telemetry data down, this is this particular piece of software. This is a dashboard from what's called FunCube One. This allows us to take that data that we pulled out of the air and analyze it. One of the things we're getting here is live telemetry. So we see the power, the bus voltages, how much power it's drawing, how much power it's generating. We can also see some of the historical. This is the live messages that they're scrolling in. And then here is some of the historical data. We can see how much power is being generated. We can see how the thing is spinning on its axes. One of the interesting things about this satellite is that they painted the outside of it 2 different colors. One side is highly reflective, one side is very, very dark. And what that did is, solar radiation pressure causes it to rotate ever so slightly in the z-axis and help stabilize it. But we can see, through the telemetry data, we can do some analysis and see that with our ground station. So how are we going to do this? Logistics. So registration for this program starts tonight. You all get an email. Go ahead and sign up and express your interest in which of the 3 departments, maybe a primary and a secondary, that you would like to participate in. We need to make sure that all 3 of those areas are covered. It will be free to cadets. There are no lab fees involved. It is a commitment, though. And I want to say this is a very complicated thing that we are trying to do. So we're trying to make it as accessible and easy to participate as possible. But at the same time, when you sign up, you have a responsibility to see it through, to commit to the team, to make sure that we meet our goals and meet our deadlines. There will be 1 mandatory meeting per month where we all get together. It's going to be a Saturday or Sunday. And it'll be organized essentially. The morning will be a class session. We will all learn something together. And then the afternoon is going to be all build time. So we will be designing the part and printing the part, cutting the part, assembling the part, writing the software, building the antenna. We will be doing hands-on stuff that day. We will try and use telepresence as much as possible. There will be 1 mandatory in-person meeting per month. But the teams, we cannot do this with just 1 meeting a month. The individual teams, the 3 teams, are going to have to schedule time together in order to see this through and meet their milestones. Telepresence, I think, is going to play an important part of that because we have, although LA County is fairly compact, we have a lot of other things going on in our lives. Traffic is horrible. We understand all of that. But I think this will help us. This will really, really help us be able to collaborate online. Online learning. Anybody here heard of YouTube? There is a tremendous amount of material that's really quite good on YouTube, for example. And so we're going to take advantage of that. We've already identified, we've built out some curriculum that I think will get us started, but we've identified some online learning that we can all do on our own time so that when we meet with our teams, we know what it is that we're talking about. There will be monthly and quarterly milestone goals. The monthly goals are for the individual teams. The quarterly goals will be for the entire project. The quarters are when all the teams, the 3 teams, come together and we integrate all of those things that we have done. So for example, in the first or second quarter, we might have the structure ready to implement the software from Mike Liu's team and attach the antenna and the radio system from Kayvon's team. It's a chance for all of us to come together and integrate all 3 of those things to make the whole product. And they will advance in parallel in quarterly intervals. The location right now, it's for the all hands meetings will likely be Whiteman. We're looking for an additional facility. This is a shared facility, and so unfortunately we have to set up and then tear down and set up and tear down. So we're trying to find a space where we can set up, leave our equipment set up, but in a secured fashion so that we don't waste time doing that. So here's what we need in order to get us to the finish line. First, I need you to sign up. Tell us what you want to do, how you want to participate. Second, we do need funding. We do have, at the moment, our first year's cost is projected to be about $3,500. And so far, we've gotten about a third of the way there. We have enough equipment and parts to get us started, which is wonderful. We do have an Amazon parts wish list. We're applying for 2 small STEM grants right now, and we're seeking some other donations. We'll see, hopefully those will come together. But it's a fairly modest amount of money that I think we can get together, and that would get us through our first year. Years 2 and 3 get very, very expensive, so we'll have to make some friends. Facilities, again, we're trying to get some additional workspace. And mentors, we're always looking for mentors, people with very specialized skill sets who will be able to help us. We want to be able to do this on our own, but there are times we know we're going to hit a wall. There's that one calculation that just doesn't work, or that one thing that we just can't get over. And mentors can really help break through barriers that we encounter. So when we come to something that we just can't overcome on our own, we really need some people that we can count on to go to and ask these hard questions to. So if you know of anyone, please let us know. Put them in touch with us. Some key takeaways for tonight. I hope I hope that you understand what it is that we're trying to do. I hope that you understand why we're doing our first year project and then have broken it up. Years 2 and 3 will be the cube. Well, I hope you understand why we're doing it. I hope that message came across. And I hope you understand how we're going to get there. Those are the 3 key takeaways. I want to foster discussions. When you go back tonight to your home squadrons, talk to the other members of your squadrons. Explain to them what it is that we're trying to do and see if you can't get them interested in it. We obviously have this recorded, so we'll send the link around as well. So if anybody missed it, they'll be able to watch the presentation. And that is all I have. Please follow us. We'll be posting all of our updates on the Group 1 Facebook site. And thank you very much. Any questions? Anyone have any questions for me? If not, we'll take a quick break. Very good.
There's
5 minutes? And refresh.
where to go.
Perfect. So just around the corner here to the right, inside the kitchen area, we have some refreshments set up. And please feel free to take a look. Oh, I forgot to demo our... Hold on. Wait. The most important part. See if I can get this thing to move. Stand by. Let's see what happens. It works. Anyway, thank you very much. We'll take 5 minutes, and we'll set up for the next speaker, Dr. Winterhalter.
So why is it?
Mike, can you hear me? Shall we start? Okay, everybody, welcome for part 2 of tonight's event. My name is Daniel Winterhalter. I'm the Aerospace Education Officer for Squadron 35, and also the Group 1 Assistant Aerospace Education Officer. So what I'd like to do is, we're going into space, we hope, in the next 2 or 3 years. And as an organization, I think we also ought to understand some of the verbiage that goes on when you do such adventures. We need to understand what goes on around our planet, how we can make use of coordinate systems, as was mentioned before, calculations we have to perform, etc. So what I'd like to do is just give a very general background today. Probably we have to, I know we have to really focus onto a lot of other issues. The stuff I'm talking about today requires that we learn more about it, about those particular subjects. So I'd like to talk about vernal equinox. As you know, today is actually a couple of hours ago. Well, at 2:58 p.m. this afternoon was the vernal equinox. I'll explain what exactly that is. But before I go there, I want to say that the real reason why we're here is because of Amanda's birthday today. I'd like to talk about the ecliptic plane, the celestial sphere. I mean, those are the kind of words that we use in everyday language when dealing with spacecraft, when dealing with missions, when dealing with astronomical issues. The length of a day. We all seem to know what the length of a day is, but maybe not so much. There is a lot of different things going on. I'd like to explain some of them. And then there's some more complications. There's always more complications. I mean, huge amounts of complications, like, for example, wobbles and precessions and all these sort of things. I'm going to throw these words at you. I'm going to explain a little bit about it. Hopefully you have questions that we can then dissect. Oops, I go to first here. Okay, so let's talk about the vernal equinox and seasons first. It's a beautiful flower. Let me tell you 5 things about, or 3 or 4 things about what the vernal equinox really is. And I think, yeah, here we go. It's the first day of spring, hence the flowers. It's also known as the spring equinox or vernal equinox. It's Wednesday, March 29 today at 14:58 PDT. It always falls on either March 20 or 21, and it marks one of the 2 days each year that night and day are the same, almost exactly the same, equal in length everywhere on Earth. The other is the autumnal equinox on September 22nd. On the equinox, by the way, equinox means equal night and day. The Earth's position in relation to the sun causes the sun to pass directly overhead at the equator. Those are the only 2 times when that happens. It is also the only day that the sun rises due east and sets due west, even on the equator. The main reason, can we turn the lights down a little bit lower? Can everybody see this pretty well? Okay. The real important thing to understand, I'm sure you've seen this many times, but the really important thing to understand and internalize is that the rotation axis of the Earth is tilted by 23.4 degrees from the plane of the ecliptic. Here's the plane of the ecliptic. This is the normal to the ecliptic. In other words, the Earth goes around the sun in the plane of the ecliptic. But the rotation axis, where it spins around this way, is inclined by 23.4 degrees. That is called the obliquity. That's the name for it. Obliquity, or just axial tilt. And I explain why this is really, really important, because of that tilt, we have seasons. Spring, summer, fall, winter. If we had no tilt, there would be no season. So let's look at this. It says here 23.5. There's slight variations, but this year it's 23.4. In the summer, this tilt is actually leaning towards the sun. And what you see is that the northern hemisphere is more illuminated than the southern hemisphere because the rotation axis is tilted. If you go to, let's go just across here. If you go to the winter solstice, December 21, it is still the same way, but now it is the southern hemisphere who has more light. The tilt, this is where the angular momentum of the planet sits, or that's the rotational axis. It always stays the same as it goes around. It doesn't move. In other words, some people have the concept that it goes around like this, and of course, and the axis of rotation goes around it the same way. No, the axis of rotation remains the same in space. So as it goes around like this. It always stays the same.
That's like a spin-stabilized satellite.
It's like a spin-stabilized satellite, exactly. So even though it goes around the Earth, the spin always stays the same as it goes around, unless you fire the rocket motors or something and change it. But that takes a lot of energy. Let's see what. Oh yeah, and so of course then when we are at the by the way, the blue line here is drawn through is the equator. So at the vernal equinox today, you can see that the Earth, the whole Earth, north and south, gets the same amount of light. It's fully illuminated. It's fully illuminated. As I said before, if you're here, not. The north gets more. If you're over there, the south gets more. And the same thing over here. It's fully illuminated on the other side here. And of course, as the Earth rotates, the other side gets also illuminated the same way. So when so that's, I just want to make sure you understand, this is where you have summer. This is when the sun is up in the sky, 23.5 degrees. If you are at a latitude of 23.5 degrees, it will be directly overhead at your zenith at noon. If you are at our latitude, 32 degrees or something, the sun will not be exactly at zenith. It will be 32 minus 10 roughly. So it'll be at closest 10 degrees or 12 degrees to the zenith. So it has obviously some very important consequences. The apparent path of the sun across the sky as we follow the sun, if you are, okay, let me just explain that picture here. We have west, east, north, and going up to the north pole of the sky. If you then follow the sun from the east to the west in the summer, the red thing here, it goes much higher like this, and therefore spends much more time on daylight. The day is much longer, as for example in December 21, when it's lower on the horizon. That's when you see it over here. So in summer, the sun's path is longest, and so are the days. In winter, the sun's path is shorter, and so are the days. That's why you have the variation in the number of hours of daylight in the day at different seasons. Somebody was asking about the zodiac. Zodiac derived from the word zoo in Greek. If you are at Earth and you're looking at the sun, this is I think in May or June, and you're looking at the sun, it actually points towards the Taurus. What do you call it? What? Right, bull. Right. Okay, it points towards the bull, Taurus. If you are close, or like today, you would be looking here. The Earth would be here, and the sun actually is in Aries. If you go further this way, eventually it'll point this way, and Gemini is over here. So that's how the 12 zodiac signs are being determined. So if you're interested in the zodiac, here is what happened. I have a really interesting little movie here from a satellite that looks at the day-night distinction, right? And what you see is this is a whole year. It goes back and forth. So here, for example, it's winter in the north. Now it's summer in the north. Now here is the vernal equinox, or just fall equinox, and it goes back and forth. I think it's a really great thing. Every back and forth is 1 year, and it's from I think a weather satellite that they use for that. This is a really cool thing. So this is the Pyramid of Chichen Itza. In the summer and in the winter solstice, people go to Stonehenge, but for the vernal equinox, go there. Look at this. This is the tail of the serpent, and it connects to the head at the vernal equinox. These dudes,
Not quite that long ago.
but a long time ago, 1,000 years ago. Well, the Mayans of Chichen Itza, I think, were 1,000 years ago. Yeah, so they knew how to build this.
Without computers.
Without computers, but a lot of slaves. So, so they know how to. They really know how. They had a very, very strong sense of astronomy, how the heavenly bodies align or not align. And this is really, I found that spectacular. Does anybody know why? This is primarily for the cadets here. Why is it warmer in the summer and colder in the winter? Who knows? Come on, give me a suggestion here.
More hours of sunlight? Keeps you up.
That's a good answer, but no.
Well, if our angle's closer this way, aren't we getting
No,
more dark?
you're the AO. Okay, so that's anybody else?
More direct sunlight.
Okay. the brass here tells me all the good answers here. Many people have the misconception. It's a very common misconception that we in the summer must be closer to the sun than in the winter. Not true. In fact, the opposite is true in the northern hemisphere. What really happens is, as people just told out loud, is that you have a higher incidence of sunlight.
More radiation comes in.
Yes, a 1 square meter, pipe of light, actually at an angle of 70 degrees will cover 1.004 meters squared. If, on the other hand, the sun sits low on the horizon, with only 26 degrees off the plane, then that same 1 square meter has to radiate and warm up 2.24 square meters. So that's why it gets cooler in the winter and it's warmer in the summer. Okay, let's talk about the ecliptic plane and the celestial sphere. Everybody has heard these words. Let's dive in a little bit deeper into it. The ecliptic plane, here is the Earth looking at the sun and see the sun swipe out a plane, essentially. And that really is all there is to it. This is the ecliptic plane. If you want to have a sun-centric view, what you could say is that it's the plane that the Earth and the other satellite and the other planets, as it were, they all go around the sun in that same plane. It's not 100% like that, especially for the very outer planets. They may have a bit of an orbital inclination, but it's very close. And you can see here, here's the Earth going around Mars. I think that's all we have, maybe another one. So, so as seen from the Earth, as seen from the orbiting Earth, the Sun appears to move with respect to the fixed stars, and the ecliptic is the yearly path of the Sun that the Sun follows on the celestial sphere. This process repeats itself in a cycle lasting a little bit over 365 days. So this is also something one really has to internalize. Some of these pictures that one sees are really spectacular. This, for example, is taken in Java. Did I get this right? Yeah, in Java, Indonesia.
It's those big ones.
I feel like a very famous politician who doesn't get the words out right. But anyway, here's the ecliptic, and you can see this lineup with Saturn here on top, Mars, Venus, and Mercury. This is the ecliptic plane. This is an incredible picture.
Would that ever happen over our area here? Something like that?
Yes, you do get lineups. Yes. Yeah. So this is actually from July 2010, and the photo is taken at sunset, looking west over Surakarta, Java, Indonesia. This is another picture of very much the same thing. You have the Earth going around the Sun, defining, with the other planets, defining the ecliptic plane. The celestial equator, this here, is actually just an extension of our equator, of the Earth equator, onto a sphere that's maybe at infinity. And when we look along the rotational axis, we find the North Star there, the Polaris, and this is called the North Celestial Pole. In fact, when you do take a picture, this is in the Himalayas, or in one night, you see how the stars, everything rotates around this one point. The old Polynesians leaving their homeland, trying to get to Hawaii, probably thought they died and went to heaven when they saw this, because it was an extremely difficult thing to navigate if you don't have that. You don't know what your latitude is. In the southern hemisphere, there is no such thing. So they did little, they watched the birds and they watched little leaves drift, and it wasn't I don't think it was a very accurate way of navigating. But when they crossed the equator and saw on the horizon this one point that never changed, they must have gone ape. This is a beautiful thing. This is a technical term. Anyway.
Years of study got you there.
Years of study. Anyway, so here is more or less of a summary of what I just said. You have the ecliptic. You have an axial tilt, 23.4 degrees. Remember that number. You have the extension from the rotational axis to the North Celestial Pole. If you go down south, the South Celestial Pole, in the celestial equator, just an extension of the Earth equator. The reason why this is important to understand and internalize is because that's how our navigation systems, maybe not navigation system, but our search systems, our search coordinates in astronomy, in many of the satellites, in planetary astronomy, they are based on these kind of pictures. There are quite a few different coordinate systems, but they're all based on that picture. Here is some of them. For example, the horizontal coordinate system, also called the alt-as. The center point, the origin, is essentially the observer, you. You're standing there. This is the point, the origin. and you are the horizon that lays in front of you or is around you is essentially the fundamental plane, and the poles are zenith right above you and nadir right below you. And the coordinates are called altitude or elevation, and the longitude is called the azimuth. Equatorial, the equatorial coordinate system. I think I made a mistake here, but the center of the Earth is the origin, and pointing to the vernal equinox is the other axis that you need. The fundamental plane is the celestial equator. The coordinates that how one speaks to it is the declination, which is essentially the altitude, and the right ascension or hour angle. And this is probably this is the coordinate system what most professional and even amateur astronomers use. They set up their equatorial plate on which they mount the telescope, and all they have to do is point the right ascension to where the orbit of whatever you're looking for is, and it will automatically follow that trajectory. You don't have to step both in altitude and azimuth. It just is on the correct. So it's a real time saver, and it's a vast improvement in accuracy and precision with which you can look at something. The ecliptic coordinate system is similar. It's either Earth-based geocentric or Sun-based heliocentric, and primarily what we use this for is to give coordinates of where planets are at a particular time, because it really, especially the heliocentric part, it is a really it's a really simple transformation from where you are to that coordinate system, and when you want to find something, you can find it. If it is, the only complication here is that if it's heliocentric, typically the coordinate center is not the center of the sun. It is actually what's called the bathymetric center, which is the center of mass of the whole solar system. What that just means is, depending how heavy all the other planets are and how heavy the sun is, you adjust it for that. As it turns out, it's very close to the center of the sun, so it's not a big difference. But this is something to look out for. There's other ones like the galactic center or supergalactic center. There is many more of that. So, but the first three are probably the most important one. That when we do talk about how to track a satellite, this is probably something we need to really understand. Okay, length of the day, solar day and sidereal day. So, how long is a day on Earth? Well, the amount of time it takes for the sun to move through the sky and return roughly to the same spot, 24 hours. Yes, you knew that, right? My 7-year-old would probably, laugh at me when I try to explain that to him. We all know it's 24 hours. Well, so what happens is, yes, in some sense, it spins around its axis, the Earth. And when the sun is in the same spot as it was yesterday, that's 24 hours, pretty close. That's 24 hours. But look what happened. Not only did it spin around its axis, the Earth, it also moved during that day, right? So as it moved, the next day, it has to actually rotate a little further. And it has to rotate by almost exactly 1 degree further to see the sun again in the same space. And that means it takes 24 hours. But if you were to look at the actual time it takes for the Earth to rotate, forget the sun, it just rotates all around. And the way you know how to do that is you look at a star. Stars don't move, right? The sun moves because we're going around it. So from the point of view of the Earth, it moves. But a star doesn't move. So you can really tightly measure when one whole rotation is complete. And that actually is 23 hours, 56 minutes, and 4 seconds. So it's less, it's 4 minutes less. Another way looking at this is if you're here and you're pointing towards the sun, also there is a star. Now this distant star is really distant, right? Not 1 AU, what's 1 AU is 150,000 miles or something, huh? Kilometer. Kilometer, yeah. We're talking about maybe 100 light years, right? And 1 light year is something like 63,000 AUs. So, so really distant. So it doesn't matter where you are in the orbit. That star is in the same place. Anyway, so you're looking at the star. When you wait 23 hours, 56 minutes, and 4 seconds, you will again point at that star. But you're not at the sun. You're pointing at the star. So you got to wait another 3 minutes and 56 seconds, and then you're pointing again at the sun, but you're not pointing at the star. Okay, that's where you need the extra time to keep pointing at the sun. If you say, well, okay, somebody might say, why don't we just use sidereal time? No problem, right? Well, the problem is we lose 4 minutes every day. And what that would mean after a while, there would be no relationship to where the sun is in the sky. You would have, half of the year you would be, the sun would be from 12 a.m. to, half a day, and the other, there would be no relationship to where the sun is. And we take this time, we're worried about this time because we need to understand the length of the day in which the sun shines, et cetera, et cetera. So we have to correct it that way.
All right, talk about the leap year out of that whole thing.
No. The leap year is a calculation, or is a correction because of other reasons, and that's we don't need to. I mean, it's an important thing, but it's not relevant right now for this. Now, don't think that this is all sort of set in stone in the sense that things don't vary. You have significant variations in the length of the day. Here is a plot. You can see this is plus, let's say here is 2 milliseconds, 3 milliseconds, 4 milliseconds, and you can see each peak is a day. Each peak and trough is a day. So you have several milliseconds per day sometimes where you have a different reading. And don't worry about that red line for now. I don't want to talk about that. But the daily deviation of the length of day in SI coordinates, in international coordinates, is defined as 84,400 seconds. And what you see here, you have several variations going on the short term, but then you also have some longer variations. So you have some beating of frequencies going on. The reason why you have these kinds of variations has to do with a whole slew of things. One of them is that you have water variations in water density, large scale water densities, or you have atmospheric phenomena that's going on. You have big icebergs falling off someplace, which may to conserve angular momentum. Remember, the angular momentum of the planet is always the same, but it may have to distribute that. Some of the angular momentum is taken away by some mass, some motion, some atmospheric features, some physical features that will change that. So you have these densities. They're not predictable. They're fairly random, but they do occur.
Are those fairly small differences?
Well, you can see here. This is milliseconds, 2 milliseconds, 3 milliseconds. So you have from half a millisecond to 2.5 milliseconds, or from 2 milliseconds. So you have these kinds of milliseconds, several millisecond time of variations. Now you may say, well, okay, so what? Well, it is a very important measure because it tells us something about the structure of the Earth and how it changes. If it was just a solid sphere with nothing moving, this wouldn't happen. There's stuff going on, and this is how we know. And in fact, we can find out what is going on looking at this kind of data. Some more complications. The Earth. What is the Earth's figures is a very important thing. Like myself, sometimes the Earth is an oblate spheroid. It's an oblate spheroid. The average radius is 6,371 kilometer. But the difference between the equatorial radius and the polar radius is 21 kilometers. Doesn't seem much, but it is significant. The polar radius is approximately 0.3% shorter than the equatorial radius. So the consequence is, because of this bulge, gravitational forces, primarily from the moon and the sun, that want to jerk it around. And also some inertial forces that produce wobbles in the angular momentum vector, in the angular momentum vector. And in other words, they cause motion of the rotational axis very much like a spinning top will do. Let me talk about the gravitational force. It produces the precession of the Earth's axis, like I said, caused by gravitational pull of the sun and the moon. The Earth's axis rotates or precesses just as the spinning top does, as I said. The period of the precession is about 26,000 years. Therefore, the north celestial pole will not point into the same star field all the time. Today, Polaris is the northern pole star. 3000 BCE, it was Tuban, a star in the constellation of Draco. In the year 14,000 CE, it will be Vega in Lyra. By the way, you know CE is the Common Era. It used to be called AD, and BCE before the Common Era was BC. This is now the new verbiage. This is one of the many precessional motions that the Earth produces. There are more than what those are just the most important one. To summarize this actually a little bit, it is very important to understand that it is not constant by a long shot. I think we understand the Earth. The orbital eccentricity varies with about 100,000 year period. Eccentricity, the deviation from circular. The tilt, the obliquity, varies from 22.1 to 24.5 during a 41,000 year cycle. The precession of the Earth's orbit varies with a period of about 26,000 years, the one I just showed a little earlier. There's also a shorter period, the Chandler wobble. It varies with a period of about 433 years. Days. That's one of the short-term things that are going on, but it's the long-term things that that really seem to be driving some very things. So when you take all this together, these slowly and periodically the changes change the amount of sunlight we're getting, for example. Okay, so if you look over here, the precession that I talked about, the 26,000 year one, this is from now to 1 million years ago. You can see each peak here is about 26,000 years separated. The precession actually has some other variations embedded in there. So you have 19,000 years, 22,000 years, 24,000 year periodicity speeding or superimposing. The obliquity, this angle that I talked about, the really important angle between the rotational axis and the normal of the ecliptic plane, has about a 41,000 year periodicity, 41,000 years in between those peaks. The eccentricity, as I said before, has several frequencies combining. The solar forcing at 65 north, in other words, how much sunshine will impinge the upper atmosphere changes. And the stages of glaciations appear to be, you have to really squint to believe that, but appear to be influenced by that kind of motion. It's a very difficult analysis. People have not yet come to entire agreement with that, with the Milankovitch theory, although it has been around for a long time. It is very important. It tells us that our climate, our climate primarily might be influenced or is influenced by the combination of all these things. That doesn't mean that the short-term climate isn't strongly influenced by short-term effects like what we do to the atmosphere. Those are like 41,000 years. We know there have been ice ages. We know there have been global warming periodically in the history of the Earth. What's happening now is not related to that. So anyway, I threw a lot of things at you. Please make sure you ask me. I'm sure you have questions. Ask me now or later. I'd be happy to talk to you. This is a lot of stuff, I know. I thank you for your attention. Questions, please.
Are some of these movements, do we need to factor those in when we launch a satellite and where it's going to be, or are these so small that they won't affect what our calculations are?
Yeah, I think they're small. The satellite that we are planning on launching will be very close to the Earth, and much of the variations that satellite sees will probably be caused by ballistic air molecules. In other words, even at 150 kilometers, you still have remnant atmosphere. You don't have collisions between the particles like in the low atmosphere, but you have, because of hotspots or whatever, you have molecules flying up. That's why if you have 150 kilometer satellites, in a few years they will come down.
Because they're being slowed down.
They're being slowed down and dive. Yeah.
Well, it's good to know what the equator is and ecliptic, right?
The what? I'm sorry.
It is good to know what the ecliptic is and what the equator
That's
is when you
yeah.
satellite
That's
and
right.
see
So
it later.
that's right. So when we build this kind of thing, perhaps since we know the approximate inclination of the orbit, in an equatorial setup, we can much easier follow and point the telescope than if we would have to step through elevation and longitude. Yes, sir.
Is there a specific time of year that the satellites, it's better to launch a satellite? Can you repeat the question?
Is there a particular time of year where it's more beneficial or easier to launch a satellite? No. Well, there is local launch site issues. For example, I don't know if you recently was a satellite was launched in the densest fog I've ever seen of Vandenberg. Nobody saw it except if you were away, like I was, about 200 miles. All of a sudden, I mean, I could see the fog, but all of a sudden I saw the. But if you're sitting right there on the launch pad, you see nothing. So, so that's the only thing I could think of. I don't think any serious restrictions are there. Yes? No? One more?
You said something happened at 2 o'clock today. What was it?
At 2:58 p.m. was the vernal equinox. The Earth was at the vernal equinox, which means the first day of spring started. At this point, night and day side of the planet were illuminated equally. I mean, north and south side of the planet were illuminated equally. Okay? Again, thank you very much.